Hello guys, this is Wei. We are Olewave channel, and we are focusing on sharing the latest speech and NLP work publication with detailed analysis. Today, we're going to be reviewing a classical paper. It's by Dr. Alex Grave, which was published about 10 years ago. The title is Sequence Transduction with Recurrent Neural Networks, aka the RNN-T transducer, which is being called by people nowadays. Why we are revisiting this paper which was published 10 years ago. I think one reason was because I think I read a lot of tutorials people wrote on these RNN-T, but I think according to what I've seen, there are lots of information missing, and some of them are not accurate in terms of the content of description. And I think most of them lack of a detailed analysis. I mean, so this is I think very important to look at the original paper so we can know what Dr. Grave was thinking 10 years ago. And by understanding his thoughts, that is important and beneficial to our own research in speech and NLP. Okay. First of all, let's start from the abstract. I will read in a very slow mode because I think almost every paragraph was very well written, very clearly addressed. So I think it's very beneficial to just check every part of it. Okay. Let's see if I can make the font a little bit bigger. I think so. Okay. He's saying that a lot of the machine learning tasks can be interpreted as transformation. Okay. All know transformer, right? Transformer was mentioned in around 2017, but Dr. Grave mentioned about this about 5 years earlier than this. He's talking about transformation, and he referred this as transduction, and he mentioned that in the rest of his paper too. It's about how to transform the input sequence to an output sequence, which includes speech recognition, machine translation, something I don't know, which is a protein secondary structure prediction, and text-to-speech. The key challenge in this is how to learn to represent both the input and output sequence in a way that is invariant to the sequential distortion. So let's say, what is a sequential distortion? So in the speech, you can see, I can say a sentence like, how are you, in normal speed, but I can see it very fast. So the input is shrinked, okay? Or I can speak it slowly, okay? It's being stretched with stretched input. And I can also speak utterance with stutter. For example, I think this is so this is also stretching the output, and the translating means that I'm really sorry, I don't know what he was referring by translating. So the recurrent neural networks, which was not invented by Dr. Graves, are a powerful sequential learning architecture. But before this work, to train the RNN, it somehow needs a predefined alignment between the input and output, so they can do the transduction. I think if you check the papers around 2010, there are lots of RNT, not RNT, RN papers. They do have to have, first tell, okay, this part input corresponds to that output, so they can perform the back propagation in terms of the learning. And this is a severe limitation, because finding the alignment is the most important, difficult thing. I think, also in my opinion, as long as you can find the alignment between the input and output, finding a good alignment, a perfect alignment, and the problem is basically resolved. The reason that the RNT is still needing to be improved was because the alignment was still not perfect, being learned nowadays, even 10 years after he published the paper. And also determine the length of the output. So in terms of the decoding or inference, and RNT you leverages a autoregressive decoder. So when should I stop decoding? Because the autoregressive thing can keep going, right? So determining the length also is also challenging. So this is why Dr. Gray was thinking about this, and he wants to introduce a end-to-end probabilistic sequence transduction system. Okay, and he performed the experiment on the TIMIT speech corpus, which is a phoneme recognition task. So let's see the introduction. I think it's also beneficial to read the introduction. The ability to transform and manipulate sequence is a crucial part of human intelligence. Very well written. This is keeping being recorded. I think that the major problem by such type of system is how to represent the sequential information. Remember this. I think he's keeping talking about the sequential information. I think this is also the difference between a speech recognition versus a face recognition or image recognition. It's not just a one sample in, one label out. It's a sequence of samples coming in and a sequence of samples coming out. And you may say, okay, is this like the machine translation happened in the NLP domain? It's not exactly the same, because you can always wait people finish typing and start to get a translation starting. Okay, because usually, because of the difference between language, you have to wait till the end of the sentence to start the translation. Okay, but the speech is not. You can see that while I am speaking, a speech recognizer can start working on recognizing what I'm saying. Because of why? If you're talking about alignment, you will see that the alignment is always between the input and output is almost kind of a monotonic or linear. So which means the future signal would very unlikely to generate the past output label. Okay, while the machine learning is different, they could. And it's very important to mention that during the taking in of the speech input, there are lots of sequential distortions. And he mentioned that the distortion could include speaker variation and the channel variation, which add the noise, accent, and also it's like there are other things coming there. The missing words, you know, for people with speech problems, they tend to omit the words in the output. Okay, and for English as a second language learner, they may not be able to pronounce the word in a correct way. So you can see this is different than computer vision or NLP. This is very difficult when people pronouncing something wrongly. Think about the traditional modular system or hybrid system. You could have a acoustic model, lexicon, and a language model. And the lexicon model defines how people pronounce each word. While in this modular system, lots of time the lexicon or the orthodox or the standard lexicon would very likely to fail when people have accent because they're not pronouncing in a standard way. And also, likewise, people will speak words in a sentence, but they also tend to express some non-lexical part of the elements in the utterance. For example, laughter, cough, or hesitation. Okay. Which all introduce some something that's not regularized compared to, you know, the NLP case. Because for the NLP case, you have a spelling correction or type correction things, which can be easily incorporated into the system to reduce these type of disturbing or distortions in the input sequence or the output sequence. And he's talking about the past of the recurrent neural networks, which was introduced before him. But he was talking about the limitation of the RNN networks for also. Especially how the input and output should be aligned. According to my knowledge, before him, nobody talks about how the input of the RNN and output of the RNN could be aligned. And he did mention a very interesting thing, which is called connectionist temporal classification, or CTC. So nowadays, everybody knows CTC. Computer vision, people know CTC. NLP guys, they usually do not use CTC. Speech guys use CTC a lot. In his definition, and he's also the author of CTC, which was published about 16 years ago, or 6 years before he published this R&T paper. In his definition, he called this an RNN output layer that defines a distribution over all alignments with all output sequence not longer than the input sequence. Of course, the CTC's output is not supposed to be longer than the input sequence because you can only expand the output sequence by inserting blank symbols, but you cannot squeeze the output sequence, okay? And it's interesting, he's mentioning the CTC as a RNN output layer. This is something I truly do not fully understand because by definition, or in his work, the CTC assume that all the output sequences are independent. Okay, and then how can he have this recurrent structure, which means the the previous, the current output is dependent on the previous output. Okay. Yeah. So this is why he's introducing this work, which is the RNN transducer. So in his opinion, I think he said CTC is a type of RNN, and he go one step further on the RNN to go from CTC to RNN transducer. So he said the transducer described in this paper extend the CTC by defining a distribution over output sequence of all lengths. Okay. Yeah, the output can be shorter than input. And also, what is more important, a joint modeling two things. I think both input and output, CTC does this. And what is more important is that the output and the output dependencies, right? So it's dependent on the previous output. And also the input output thing is kind of slightly different than the CTC. We will see how he did for the RNN-T transducer. He also referred to another discriminative model. So yeah, every algorithm mentioned in this paper is a discriminative method or discriminative sequential model. He talked about CRF, conditional random field. For those of you who are interested, I think you should check the online tutorial and or read the original paper, which was about 20 years ago. So I can give you a very quick overview of what is CRF. So it's a discriminative model. So it models a given input, what's the probability of the y, and this is a sequence. Use the vector to represent sequence. Okay, but different than when you talk about CRF, you have to mention HMM. Okay, the CRF is a discriminative model. I use a D to represent discriminative. Okay, and HMM is a generative model. HMM, it tries to model the probability of X given Y. So the X is the observation or a feature, and then Y is the hidden variable. Okay. And I didn't put the vector sign over here, so that means the HMM has a very strong assumption, which is that given the current, the future and the past are independent. Okay. Let's go back to CRF. So it assumes that all the output are not independent of each other. So you can see compared to HMM, yeah, it is a discriminative model. It's not a generative model, but you can see it's trying to model the whole sequence. So the thing is, anytime you throw away the conditional independent assumption, your model became very big. So training the CRF takes a lot of time. And another important thing is that training the CRF, I think it cannot be parallelized. So it cannot be thrown onto the GPU to train. So nowadays you do not see anybody using the CRF, but the RN people can, do the batch mode or do it in a parallel mode. So it works well with the GPU, and the RN trains relatively very fast compared to CRF. So it's a big success. Okay. So here are some notations he made about his RNN transducer. First of all, I will use speech to let you understand what he's talking about. Okay. First of all, he talked about the X. Okay. X X is a speech signal sequence, speech sequence. Or I think at his time, people do not usually take the raw speech sample as the input. Although nowadays, I think nowadays people do use raw signal. And it's very popular to use raw signal. I think, but at his time, you can see he's talking about the MFC coefficient or MFCC. Indeed, he could also use filter bank. I think nowadays also lots of people using filter bank. For those of you who are not knowing what these are, just Google them. Okay, I want to explain this. But you can regard the MFCC or filter bank as features extracted from the raw signals. Okay, and what is the output? Let me show you the notation over here. So the vector y means text sequence. Okay. But indeed, I think in his work, it's phonetic sequence. Or nowadays, the most popular thing is the word piece sequence. Okay. Word piece sequence. Or some people use letter. If you're doing the Mandarin speech recognition, this could be character. So the character means, for example, I think you all know the word like ni hao, ni, you, and how. These are 2 characters. Okay. There are many ways of representing the y with different unit. So we call this unit. These can be regarded as the unit or token. Okay, call that token. This is not what sequence. So, and what is the y star? Y star means the set of all sequences. What does that mean? So it means first of all, there's a space y. And how do people, how he define the y? The flower y? I think he defined y. It's not all the units. It's still. Anyway, he called this output space, okay? It's a space of output. Well, I can only explain up to here, okay? And the y star means that of all sequence over y, all sequences over y, okay? So I assume that, and you can see in the following, okay? And then he defined I think the output space means the stuff he is actually talking about. The y can be the space of phones. Okay, so suppose you have 39 phones. So it's like going from A and the T, AY, and Z. 39 phones, not letters. Okay, usually English has 39 phones. but the y bar is y union with the blank signal or the null signal. Okay. Okay. And then you may ask why he wants to add this. So if you are familiar with the CTC, you would be understand why he's doing this here. But he's definitely not trying to make the length of the. He's not trying to. So let me ask you this question. So what's the purpose of extending the output space? Okay. So does that mean he is doing the same thing as he did in the CTC, so that the length of the expanded output y is equivalent to the input sequence length t? Is him? The answer is no. Because he's just using this for the forward and backward algorithm. We will see in the following description. Okay. So he did this expansion thing here, and so in this space, y star can be expanded. Sorry about y star can be expanded. I don't think you can see it here. Okay, so I do this. Y bar star. Okay. This is so all the sequence you might have y1, y2, y3. This is one sequence. Okay. And the y bar is one expanded one, could be this. Okay. And you can definitely understand this. So whenever he wants to say, okay, given one input sequence, I want to estimate the probability of any output y, and the y belongs to the sequence set. Okay, the set of sequence. What's the probability of this? So you can definitely go from the summation of the probability of the alignment given the input. So what is the alignment? It's mentioning here. The definition of the alignment is, so given any input, okay, the A to X has an alignment. Okay. I think I want to correct myself. Maybe I'm wrong, but I still think the purpose of expanding this is trying to make the length of the U to be equivalent to T. Okay, or U plus the expansion, so it can be equivalent to T. So this is why you have the alignment. Alignment is that anyhow you want to expand the output sequence so that it has the same length as the input. Okay. So you can see if you read the CTC paper, then you can see that you can have arbitrary amounts of blank symbol or null symbol inserted in between the labels in the output sequence, okay, in order to have this to be equivalent to have a size of t. So here you just get all the possible alignments over here and sum it all over the alignment. Okay, all the possible expansions this means. So I think you understand this. Let's move on. But what do you see the problem is? Well, calculating this is almost impossible, okay? There are tons of alignments over there. How do you calculate the probability of the alignment given X, and how do you count all the probability of these? It's a headache. Thank you to correcting me if I were wrong. Okay, thank you to Baum and Welch. They come up with this Baum-Welch algorithm, which is also called a forward-backward algorithm. Back in 1960, correct me if I'm wrong, maybe 68 or 60 something, which about 60 years from now, okay, they come up with a way of summating all the possible probabilities from this alignment in a fast and computable way. Okay. But Dr. Gray would explain the forward algorithm in the next section. But in this section, he introduced two networks. This is something I think a lot of the tutorial are making mistake here, or wasn't explaining the details here. Remember, whenever they talk about RNN-T, sometimes they say, okay, they just draw this. Okay, here is the current input, and here is the output of the previous time point, and this is the output Y. It's wrong. It's not just one network. It's actually two networks. Okay. The first network is called a transcription network. The second one is a prediction network. And because the prediction network is relatively simpler, he talks about the prediction network first. Okay. So what is a prediction network? So it's actually, let's first talk about the prediction network. It's actually a flower G, which takes the output Y. I draw it from there to there. Okay, this is weird, but you understand why I draw it in this way, and generate the predictor vector sequence G. Okay, how does this work? And you can see the equation. I can't see the equation number. I guess it is the first equation. No, second equation. So the Y hat U means this is actually, he called this input sequence, but it's still the labels of the speech recognition. Okay, in the speech recognition, it's actually in his work phonemes. Okay, phoneme labels. So what he was doing here in a simple RNN network is that I would draw in this way. I draw downward. Okay, so this is the current sorry, I prefer to draw it always upward. Okay, let me draw this way. So this is the input, or the current prediction, or the previous prediction of the y by u. What does the u mean? U means is currently you only know either training or decoding or inference. You only know from label 0 up to label u. You do not know anything beyond this point. For instance, u plus 1 to capital U, you don't know them. Or in the training, you don't know them. In the inference, you haven't got them yet, because in the decoding is also left to right, autoregressive decoder, you don't know them. Okay. And it passed through a matrix. Okay. And then you got the another matrix, WHH. What is HU minus 1? So you can see I call this U. This is U minus 1. Okay. And then you also have a BU. Okay. BH, BH is bias, it's trivial. Okay. And after you get this, you pass through a flower H. Is a nonlinear operation. It could be sigmoid, could be ReLU. Okay. Then, sorry, I prefer to put the H here. I think I still prefer to have the H here. Sorry. Okay. And then how do you get the GU? GU, you pass that through another. No, I can draw this. Another network, which is WHO plus BO. And then you got what? So this is a linear operation. Okay. Got GU. Okay, GU is your predicted prediction vector at the time u, not at the label u, or at the index u. So u is the index. Okay, it's not the time index. Okay, but you always start from 0. And then what you say? What happens in the next label? Okay, then I can draw the same thing for you, because the Dr. Grave didn't draw this. It's still WHH, and it's still BH, but over here is still WIH. The matrix never changes. Okay, when you draw this, and then but this one became U plus 1 label. Okay, U plus 1 index. You see YU plus 1, right? And then after you got this, it's the same nonlinear operation. And then you got H U plus 1. And then you got the WH0 and the B0. After you add this, you got a GU plus 1. So you can see that this is what you got. Okay, you got a sequence, right? And this is your actually input to the prediction network. And you have a what do you call that? You got to input a sequence of this. And the key things here are these hidden vectors, H's. Okay, hidden vector sequence. Yeah, drawing's not very good. And You may ask, I understand the Y and the G now, output, input, and how do I come up with the H? Okay, let's see how the hidden vector are being obtained. Oh, before we go to the hidden operator, let's say this. He talked about this in the RNN style, but people will find that, okay, Jorgen found that LSTM works better than the RNN-T. But nowadays, nobody uses our LSTM. People will always use the transformer or conformer. I think it's like this is LSTM was about 10 years ago, and nowadays it's all being replaced with a transformer. And what is even better is conformer, okay, for speech. I do have a paper reading on the conformer and the transformer. Feel free to search these two keywords in my video list. You will find them. So I will not go into the details of LSTM, but all you have to remember is that it still tries to come up with a hidden vector, but he didn't care too much about the terminology. He only talked about, okay, remember in the RNN, the HU is supposed to be obtained by looking at this first equation in the equation number 2. But in LSTM, I think he should change the N to U. I think it's a typo thing. It's obtained in a slightly complicated way, but everything here is differentiable when you're running the back propagation. Okay, that's a slightly sophisticated. Okay, then he talks about the transcription network. I think transcription network, although the equation is like this, is actually slightly sophisticated than the prediction network. So how does that work? First of all, he talks about this network to be bidirectional RNN. But of course, you can imagine that you can always replace this with a bidirectional LSTM, or nowadays, or using a transformer, same thing, okay? And then you can see how does this work. The first you have the backward sequence, okay? How does he obtain the backward sequence? But let me use the backward sequence, this symbol, to represent the backward sequence. So this is a backward sequence at time t, okay? So this one, you draw this, I think, anytime, anyway, you always have a input. So input could be MMCC, okay? I think he needs to work on the symbols, but I understand this could be X, should be XT. I should be converted to XT, okay? Or he might thought that, okay, he did some I here, but I don't think he actually explained what is I. I think he mentioned this is the speech feature, okay? Or say, at the first layer or the first block of the bidirectional LSTM RNN, the I is X, but in the upper layer, so it's no longer X, it's some intermediate feature, so it's not X, okay? Okay, so the input is always IT. It passes through the WIH backward matrix. And then what, didn't draw it very well. What goes from the past, sorry, what goes from the future, h of t plus 1. This is WHH backward matrix. And have these type of, do you have a bias? And after he do this, you see he has a flower H, which is a nonlinear operation. Then he got what? He got a, this is a backward, okay, he got a backward hidden vector at the time t, okay. Same thing happened here. Suppose you want to go forward, okay. Forward is like this. I hope you can draw this with me, because this is kind of interesting to go step by step other than do this from a slide, okay. You see, they use the same input IT, okay. See here, I should draw in a straight line. This is the WHH forward, okay. This one is different than this one, okay, because one is a forward and one is backward. And here they use WIH forward, okay, and the bias. And what you got here? He got a, what do you call that? A linear operation. And he got a h of t forward. You see? Now you got the forward h of t and the backward ht. And then the next step would be combining these two through this. One is a WH. The thing is, I think he should well, he used O is okay, but remember that okay, if you're at the final layer, this should be f of t, okay. But it's the intermediate layer, it could be OT, okay. Let me use O, still use O here. I hope you understand the difference between the O and the F, okay. This is WHO backward. Then you got this. Got summate together, and plus a bias BO. You got what? This is a linear, no nonlinear operation. Okay, this is called OT, or final layer is f of t. Okay, then you got the what did he call this vector? He called this transcription vector. Yeah, this is the naming is very unique. Nowadays, I think not a lot of people call this transcription vector. Okay. Yeah, he talked about that you can replace this with a bidirectional LSTM, and it's supposed to be better than the RNN. And he talked about output distribution. So finally, he got a prediction vector G at every time U, and he also got the transcription vector at the time T. Remember, this is a vector, okay? So when you talk about a vector, it's a size of k plus 1. If he's doing the phonetic, if he's doing the phonetic classification or phoneme recognition, the K means the number of phones, which is 639. The reason he has this +1 because he inserted or added a null symbol here. Okay. You already added the 0 index is null vector. So this is why he can say, okay, suppose this is a location K, then he named this a GU to the K, okay? And if you have a element here, he called FTK, okay? And he use this equation, okay? This is a definition. If you're familiar with this CRF, you see people do this a lot, or even suppose you're doing maximum entropy or learning these type of things, MMI training. Maximum entropy training. You see this a lot. So this is a normalization operator. By doing this, he could get this probability. It's a value between 0 to 1 and the given time t and the output index u. What's the probability of the output label k? And k belongs to y bar. So what does the y bar mean? Let's see. I think I read. So yeah, y bar means it's a set. Okay, the k belongs to the sequence. No, the label set. Okay, one of the phonemes. Okay, he then simplified the notation. So this is also just a terminology, just not to type so many things. This one is this. This one is this. This is very important. We will use that in the following stuff. If you need a break, just pause the video and come back. I think I'm good doing this. And also, so you can definitely see that this model is descriptive model because this is a posterior probability. So you never calculate the conditional probability, okay? So you may ask why he wants to calculate this, because he always have this prepended label, okay? So he has to calculate this probability. You also ask, this one is important. The set, can't see this, sorry. So the set of possible paths from the bottom left to terminal node in the right corresponding to a complete set of alignment. Yeah, I think it's important to let you guys see the figure 1. It's difficult for me to draw this. I will just use them. So you can see that the x, or the horizontal axis, is the time, and the vertical axis is the label index. So you can definitely see that the speed recognition, or in the training phase, especially, let's first look at the recognition phase. He wants to find out a path, for example, the red path, which has the highest probability. So whenever he finished going from the starting node over here to the ending node out here, he could say that, okay, the decoding is finished, the inference is finished, here's the best path with the highest probability. And you can see this is the U this is the output label he got. You can see that, especially at this time point, the output label does not change. It keeps repeating itself. But at the time t equals to 3, the label jumped from this one to that one. And you can see that eventually the output label sequence has 4 labels, but the first label is always null label. So the output has 3 labels, okay? And in the training, he wants to resolve the calculation of the probability summation, which he mentioned in the equation 1. So this is the most important thing in the training phase, because he first have to get this probability of this sequence, okay? And it's not a probability of a certain label with the conditional independence assumption. Is the probability of a output sequence given an input sequence. It's very sophisticated to compute, because let me explain this, mention this again, because he break down the sequential probability into a summation of the alignment probabilities. But there are so many alignments, so calculating this will cost a lot of time. This is why he's trying to use this Trellis to explain the situation and try to start to talk about his forward and backward algorithm here. Okay. Yeah, that's what he's talking about. Yes, and I want to mention this again. I'll go back to here again. So you want to go from bottom left to the top right. Okay, this is called the bottom left. This is called the top right. Okay. I hope you're with me, because I'm explaining this in a very slow speed, because most of you are not familiar with the forward and backward algorithm and the CTC paper. Okay, what does he mean over here? So first of all, he come up with a set. Set means all the possible paths or all the possible alignments is being represented by this. So this is all the possible sequence, and this is the joint operation, and the y, the b inverse b of y means that the expansion operation of the original output sequence. Okay. Well, this has way many. This has all the permutation of the y. Okay, but these are the likely y star. Okay, likely ones. So therefore, every alignment would have a probability, and this would be all of these probability would be used to sum to obtain this. This is the key. This is the key. Okay, then and to resolve this, first he wants to resolve this question: how do we compute this probability? So, for instance, you have so let's call this T, okay? This is the TU. How do you compute the probability or the posterior probability at time T and U? First of all, he started to talk about the forward and backward algorithm. First of all, he defined the forward variable. Sometimes people call that forward probability. I think Dr. Grave here was more accurate. I think forward score. Sometimes you can call it forward score. I used to call that forward score because it is a score. Using a variable, I think it's not a good term, but it's okay. So to compute the forward variable at the time t and u, you have to get the t minus 1 and the u, and also t and the u minus 1 first. Sorry, I didn't write it as well. I hope you're with me, okay? So if you're familiar with this dynamic programming, if you've done lead code, you know what I'm talking about. So it's about, if you want to calculate the probability over here, because there are only two possible paths that can reach to this node from these two nodes, okay? So all I have to do is I can use the forward variable at the here, which is this, alpha t minus 1 u times the probability of, let me call that phi or empty. I would call it null t minus 1 u. This means that there's no new output coming out. So it's still output the same output at the time t compared to time t minus 1. Okay. And then here it means that, okay, I go from here to there. Okay. And here, because from here to here, t does not change, right? But I would come up with a new output, okay, which is k, okay? Remember, you see his notation? The YTU is a vector. So given all the k, for all the k, it will just add on top of this, okay? It's a vector. I hope that you're with me. I'm sorry I can't answer your question, but I guess this is kind of straightforward. So this is going from, and what is, let me write down what this represents, okay? This is actually equivalent to probability of u, yu, t, u minus 1. Okay. Right? You see? From here to here. This is exactly the probability over here. And what is this? If you check the, let's check the probability of the definition here. This is equivalent to probability of null sequence minus 1u. So that means when you go from here to here, this is a red. You can see that. So all you have to do is to just add or times the probability of empty at time t and u. Okay, is that clear? Hope so. Okay, and here's a homework for you. Check whether this is correct or not. I want to explain it. Very straightforward. An initial condition has nothing to worry about because you cannot start from 0. Otherwise, everything would be 0. Okay, I will start from 1. And this one, I think I will just try to also explain from here. It's same thing, okay? So we just explain alpha, but let me use can use another pen, use the blue pen, okay? Okay, this is good. So also T and U, we rewrite using this color. So this is T plus 1 U, right? And this is T U plus 1, right? And you can see the backward variable comparatively is equivalent to the summation of two terms. The first term is going from T plus 1 U. This one is backward. Remember backward. Although the arrow is going from this way to this way, you go backward. Backward, you can see the output does not have new output. So you just have to handle with the null variable. Similar to this one, the alpha one, you do this, right? You time the probability of phi given T plus 1 and U. Also, you have the backward from going from there to here. And you have this probability of anyways, you have this type of YTU, okay? Is that clear? Hope so, okay. I think it's not correct to write this here. Let me double check this. Yeah, this is a probability of YU given T and U minus 1. U plus 1, sorry, U plus 1. Okay. So, and you do the homework of this. Initial condition has to be this, right? So here is something you want to think about. At any point T and U, the product, this in the output lattice is equal to the probability of emitting the complete out sequence if YU is emitting during transcript step T. This is understandable, right? Don't say his English is not clear to you, but you have to read it, you know. It's hard for me to break down the English into parts and make it more simpler. I think this is the best I can do. Just think about this if you can get this, okay? And eventually, he talked about the loss, okay? You want to maximize this, so in order to minimize the loss, okay? On the target sequence. And then because of this, let me know if you can understand this. If you're familiar with the bomb wedge algorithm or HMM or even CTC or even the dynamic time warping algorithm, you understand this. So when you have the forward and backward algorithm, like Dr. Graves said, the probability is equivalent to the sum of these over any top left. Where is top left? This is top left. This is the bottom right. Any diagonal, for example, let me use another color, okay? There's a red. Red is okay. But this is a diagonal, okay? Any values summated over this diagonal. okay, equivalent to this probability, or any diagonal, this diagonal, or this diagonal, or even just this node is equivalent to this, okay, or at this node, okay. And then, because you want to train the network, right? You want to compute the partial derivative. So the first of all, he computed this, okay. So this is a log x, and then you come up with a 1 over x, okay. You put it over here, but whenever the k is equivalent to yu plus 1, you come up with this times this. But if the k is equivalent or the output label is empty, he comes up with this. Just check the equation 16. Sorry, not 16. This equation, not 16 equation. This is a homework for you. Just check the equation 18. Okay, you will get this. And then by applying chain rule, okay, if you're don't know how to get this, check the chain rule, okay, of the taking derivative. Then you get this, right? And this is the chain rule, okay, easy to understand. And this is the summation of all the possible k, okay, all the possible k's. Same thing for the transcription vector and the prediction vector, same thing. Okay, you can see same thing. This is the transcription vector. This is the prediction vector. And these are derived from here, right? It's being calculated. And then these two is even simpler. If you check, I will leave a homework for you, okay? Check the equation number 12 and see if you can obtain this. Is that from equation 13? Am I wrong? I think it's equation 12. Oh, he's right. I'm wrong. It is equation 13. You go from equation 13, and then you can get this. If you don't know how to get this, then check how to get the derivative of sigmoid. The sigmoid functions derivative. Just search anything on the Google, okay? So you can see these things are resolved too, okay? So eventually, what he resolved, let me use this pen. Eventually, he resolved the derivative with regard to the transcription vector and the derivative of the prediction vector. And because you see the prediction vector is defined like this, by applying the chain rule, so you can see during the backpropagation, when you get the error at the transcription vector, then you can further running a backprop to obtain the error at the h of t forward and backward, so that you can update these matrices. Clear? So the purpose, you can understand, the purpose of the backprop is that you go down to very, very bottom, so you reach these intermediate variable, you obtain this error and use this error to update the matrices, or because this is a nonlinear, right? So you can see it will also update the parameters in the nonlinear function, nonlinear activation function. All right. Let me just write that further down for you. So going from the GU, it will further go to the matrices and the bias factors and the parameters in the nonlinear function. So this is how the neural network gets updated. Okay. And he's talking about I think leave it to the homework to you. Okay, this is he's trying to reduce the computational cost. Now he's talking about testing. So what is testing? It's more about the inference in the machine learning. Okay, let's take a break if you want. So the purpose of the inference is that inference or testing is that I give you a input speech feature sequence X, and what is the output sequence? Okay, so basically I think it's about getting the maximum probability of the sequence given the input, and remember that the Y belongs to the Y star head. Okay, and let me just try to make a note here. And I think initially, or the raw output of the Y includes these null or blank symbols, but it's easier to just further squeeze down so you can get a human readable output sequence. Okay, and then to do this, because he's not getting the output sequence in one shot like people do in the non-autoregressive model nowadays, he's doing in this like an autoregressive style. What does that mean? He would always go, suppose you got a time signal from 0 to t, it would also go from not 0 to, I think it's 1 to t. Go from 0 to u, okay? And then next time he will go definitely move forward the t and also move forward the u this way or this way, anyways, okay? Because it's a trellis, okay? I think I'm not writing this in a good way. Let me rewrite it. It's don't want to draw it again, okay? It's more like a trellis. Although this trellis was being used in training, but it can also be used to illustrate stuff in the inference, okay? So let me draw this. So you got you can get the decoding result up to here and there, but you can also start to use the BFS algorithm to search the next possible nodes from the current nodes, right? This is how the decoding works. But he was only talking about one of the methods. I think it's a vanilla beam search algorithm. It's called beam search. What is beam search about? I recommend you take some time to read the algorithm one. So for those of you who do not have the background of Bradford search, check the Google, okay, to learn about the BFS. Here he's implemented more like a stack decoder or maintain a stack. Anyways, the A he talked about is more like a candidate path pool, a pool of candidate paths. B is like unbest path up to now, up to T and U, being maintained. Okay. So you can see that he's always trying to expand the pool of candidates, and starting from there, he would just search the next round of or set of A, and then whenever he found, okay, this is a good result, I will put them in the or update the embed path. Okay. I can give you a fairly straightforward explanation to the algorithm one. So first, this is initialization, and you can see this is the outer. This is the outer end for. Okay. It loops over the time, and you can see that at each time T, this is at the time T, okay? He would check every path in the candidate pool and see how could he update the probabilities. Why? Let me ask you this. You can pause the video to ask yourself why Dr. Graves has to upgrade the probability of PY when he moved from T-1 to T. Okay. Okay. After you pause this, let me tell you, because remember in this Trellis structure we talked about, when you the probability of y yu at the T and U is not equivalent to the PYU T plus 1U, right? This one probability and this probability are not the same. Actually, it's this probability and this probability are not the same. So he has to update all the probability of the y in the candidate pool because the time has changed from T-1 to T. How he changes? He leveraged a, you can call that forward algorithm or Viterbi algorithm. You can see that it's very easy to understand. This one means the prefix of y, okay? He just say any y's probability is okay, any probability y, remember this. Let me show you this. Let me ask you this. So when I go the u, suppose u does not change, I go from T-1 to T. to get the probability of this, what do I do? Remember the forward algorithm? So it's the probability of the yu at t u is equivalent to the probability of yu t minus u times, this is phi, okay, empty t minus 1 u, right? This is exactly what he's talking about over here. Let me tell you, this is exactly he's talking about here. All right, and this is a because he's doing, I think he's doing this on I think I got the idea correct. But I won't go into details because you can see that this is how he defined this over here. This means that okay, the prefix u, yeah, I think it's slightly sophisticated if you just look into the detail of the math, because even he wrote this like this. This is a vector of probability. So it depends on whether the y. So you can see that the y can be equivalent to k. Okay, the specific label at the time u, and then he has to do this type of summation, and this additional sign here meant he's doing the forward algorithm. You just have to add the additional probability term. Okay, and the next step is to how to add the path into the embedded list or update the embedded list. So suppose this B already has a embedded list. Okay, what does this mean? So B contains less than W element. W is the size of the embedded elements more probable than the most probable one in the A. Okay, it means the B has some pools or candidates, but he found that okay, in the candidate pool A, there's something better than the B. Okay, and or in a short word, B. So suppose there are less than W or W elements in B, but whenever I put the most probable element in A or the best path in A into the B set, the B set would get better, or you get a better embedded list. Okay, and then you set this and remove the Y from A. This is standard operation of BFS, and then you do this. Okay, this is the operation of t minus 1 to t. Okay, is that clear? Hope so. And then you add this one to B. Okay, so the embedded list of the B is updated. Then the next thing is you start this loop. Let me use another pen. Remember in the BFS, when you remove the one node from the stack, you need to expand the possible candidates from this removed node. Okay, this is exactly what the Dr. Gray was doing here. So for any label in the set Y, it does not include the empty label. So you basically just do this. So remember, this is going from this is u, this is t minus 1 to t, and this is like going this way. This is a t, this is a u, probably u minus 1. Okay, this is a u. Okay, this is this operation. Okay, clear? I think so. Then you add this expanded or extended, not extended, the longer path to A. You see, this is how the decoding is going forward, because before this time point, the length, all the sequence that all the sequences in the set A are sequences with length less than u. Okay, now this is the occasion that a sequence which has length of u plus 1 being added to the set A. Okay, and then after doing this, you get a better, or you get so whenever you remove an candidate from the A, you just start to span out from the removed node. Okay, and then you keep doing this until that, okay, you find that, okay, B has enough amount of best path, and no path in A can yield better path. So I would stop. And then eventually, I think this might be necessary. So you move to fix the size of the set B to be W or in best. And then eventually, this is important. Eventually, you can see Dr. Graves normalize the probability with the length of the Y. Why? Because he mentioned that this is a very common practice when you do this in the machine translation or in the hidden Markov model in speech. If you're familiar with the generative model and you're familiar with the stack decoding in the HMM-based speech recognizer, you would see that it was having a we call that length normalizer over here. Okay. All right. I hope I explained this clearly. Okay. Then move on to the experimental results. I would say back in 2012, the result wasn't very perfect because I think at that time, the best system without the language model, yeah, some people do add a phonetic language model on top of this to get a better result, but this is also, I remember in my memory, this is also Dr. Hinton's work. Dr. Dahl get a result which is very close to 20% error rate by leveraging his proposed method, Boltzmann restricted machine RBM. But Dr. Graves' work, if you see the CTC, this is my own personal opinion. CTC never works well, but it's probably the most simple or straightforward model for speech recognition. You get 25%. It's not a very good result. But Dr. Graves did show that by leveraging the transducer, when you remove especially the conditional independence between these output, you can get a very significant amount of reduction in terms of the error rate. And you can see the log loss reduced significantly, and it runs less amount of epochs. Okay. Of course, if you're just using the prediction network, I think GU, right? It won't be working well. Okay. Well, he did show in the appendix. This is the alignment he obtained by using the RN. You can see this alignment is mostly monotonic. When I mentioned that the monotonic, it meant it always moves forward. It does not go back. So it always moves from the bottom left to top right. It does not go backward or then forward. You see, or this is not necessary. I don't think it will go back or something like, how do you say that? Maybe like this and then this, right? It might be also a way of alignment. I think sometimes machine translation, they could have alignment something like this, right? It's not monotonic, but the speech is mostly monotonic. So this is you see this alignment is going from this way to that, this way, okay? And I think he also showed that the difference between the bidirectional bidirectional alignment over here versus the only forward alignment versus the only backward alignment. You see, this is not very good, especially the backward. You see, right? So this means that if you're doing the speech recognition, and if you happen to have a way of always going from the future into the past, you won't be getting a very good result because you see the alignment is not very, very good. But you definitely can just use the forward alignment or the forward variables. It's okay, I would say. It will still do the speech recognition. So you can use this is called a unidirectional RNN or LSTM. It's okay, but it won't be working as good as the bidirectional. This is better. Okay. But you may ask why the speech would be dependent or why the backward matters. Nobody has a good explanation to that. Which means that when I say I want to say I want to go to school today, it means the goal word would be affected or is dependent on the future word today. It's to some people it's understandable, but to me it's not very, very understandable. But this is what the data shows. Okay, the current is dependent on the future. I think this is also the reason why the CTC doesn't work well, because you see the output are fairly dependent on each other. All right, I will stop here. Okay, thanks for watching our presentation. I think today is a very long one. I hope you get the most of the part of the RNN-T transducer. And I will see you next time. And if you really like our video, please subscribe. And I will see you next time. Goodbye.